So our next speaker is Giles of Myrtle.ai. He's head of marketing, and he's going to talk about realizing the enormous potential of FPGAs for machine learning. Giles has built experience design, sales, and marketing roles of ASIC, FPGA, and IP companies. Since 2018, he has focused on FPGA acceleration for machine learning applications, and he joined Myrtle.ai in 2019. He is located in the UK on the Isle of Wight, so found that during the break.
Thank you. Yes, thank you, Mike. So as Jeremy said earlier on, the GPUs have dominated the training space, but we do see a lot more opportunity for FPGAs, hence the title here. So as Mike said, my background, I was originally a hardware designer. That was a long time ago, so I apologize for my lack of technical expertise in the meantime, but I've been in FPGAs now since 1994, which was one of the earlier years, and seen them progress from essentially an ASIC programming tool to what is now a very strong contender in machine learning. So we've all seen the trends in AI. There's a lot of talk about Gen AI and the massive models that are being used for that. But there's also a lot of work in the smaller models, and a lot of the companies that we're talking to at the moment are in that smaller model space. Constantly evolving, still a focus on energy consumption, sustainability, and for all those reasons, I think FPGAs really do have their place, and my role here today is to try to position that. So as a company, we are a small startup based in Cambridge. We have about 25 engineers, and we focus on optimizing machine learning inference for scale applications. We partner with the high-end FPGA companies. So yep, I've got the name Altera up there. They've recently changed from Intel, just making sure I'm up to date. AMD and Acronix. So we work closely with all those three, and we've developed a number of applications, particularly in the low latency space, but also cost reduction, throughput improvement, and so on, as some of the examples that you can see up there. So during that process, we developed a comprehensive IP library for all those applications which we can reuse. And we focused more recently on three things. One is an application we did for Facebook, which was optimizing memory use in an FPGA for inference. Another one is in conversational AI, which is a big area upcoming with a lot of focus now on the few hundred milliseconds target time from speech to speech. That is speech to text, then some kind of large language model to derive an answer, and then text to speech to deliver that answer back to the person who asked the question. So that puts the focus on implementing a lot of machine learning in a very short latency. And again, that's what FPGAs are really good at. So those two areas. And the third area I'll expand on later on. But first, I've tried to do here, and this is a very contentious area, isn't it? Trying to do a comparison between GPU, custom chips, and FPGAs. So this is perhaps a simplified, my version of this. GPUs, obviously designed for massive parallel processing, originally for graphics processing for games, and realized that that was actually a very good architecture for AI. And I think Jeremy again mentioned CUDA earlier on. That's a fantastic tool which has encouraged a lot of people to use GPUs for AI. And the investment they are making is going to be hard to beat. But what I want to come on to now is how we can diversify from GPU platforms. They are power hungry for sure, and that is a big issue. And they also have a limited minimum latency, the amount of time it takes to launch a kernel, and then on top of that, do some meaningful work. Does set a minimum latency, which can be an issue in a number of cases. However, they are extremely good for training. They have massive throughput, and they're very good at handling large models. Custom chips, that's where I came from originally, highly optimized for some model types, but they really are specific to certain models. And you're going to need a large amount of money and a lot of patience to wait for getting that chip back. And that's really not viable very often in today's world where things are evolving so quickly. Nevertheless, really good for high volume applications. Then we look at FPGAs. Well, latency is a key advantage for FPGAs. They can also be very energy efficient. And of course, the flexible hardware in FPGAs lends them into the fast-moving ML world where models, operations layers are changing very rapidly. However, the red mark there is against the hardware design skills required. So a lot of companies that are trying to use FPGAs are having to, or feel the need to recruit, manage, train, and maintain an FPGA, an in-house FPGA design capability. That is limiting their application, and that's one thing that we at Myrtle.ai have been trying to resolve. So FPGAs then, really good at real-time applications. Conversational AI I mentioned, we'll talk about some more later on, where latency critical and low power for edge applications as well. This is not my graph. This is a graph that NVIDIA put up in a webinar not so long ago. This positions, in their view, how GPUs and FPGAs fit in this market. So the crossover there is 10, 30 microseconds, something of that order. It's not specified on their graph, but results from benchmarks have shown that's about where it is. And it's very clear that GPUs have that throughput capability. So if that's what you want, training applications, then a GPU is a good platform. But if you want that low latency, below about 10 microseconds, you're not going to get it from a GPU. So you do need to look at FPGAs. We talked about the challenges of implementing FPGAs. Well, the first one is to optimize that design for the model and the priorities. So your priorities might be latency, maybe that you have a minimum throughput requirement, energy issues, rack space, all those other issues that people are looking for, and cost is a big driver too. But in order to optimize that design, once you set those priorities, you need to bring together your hardware designers, your software designers, and your ML developers to optimize that implementation on that FPGA. So there are all sorts of trade-offs that you can make between accuracy and real estate, i.e. cost or performance as well. And putting those three together is really the only way to achieve that. Most companies don't have that luxury of having all those three disciplines that can work together in that organization. And the other thing is that even once you've implemented a design, and we're talking to some companies that have handcrafted a solution for machine learning inference using the DSP blocks in an FPGA, for instance. Well, that's great, but it's only going to do that application. You change something, and you're going to have to generate a new bit stream before you can even evaluate the impact of that change. So what's really needed is an environment which an ML developer can use without access to FPGA design expertise, where he can build that design, iterate it, evaluate it, and implement it all by himself. So that was our target. We talked about optimizing the design, talked about what are we optimizing for, and then optimizing for which FPGA family and even which device within that family. So all those resources that you have in FPGAs, the different FPGA companies have identified families for specific applications, some of which are AI, some are more generic. They all have different balances of calculation blocks and memory and networks and so on. Our objective is always to keep the weights on chip. That's the only way to achieve the latency which FPGA is so good at. But we can balance things as we heard before in one of the earlier talks. We can talk about quantization. We can talk about the use of sparsity, and that can be applied to different layers. It can be applied to weights, activations, and so on. So there's a whole host of different options that you have there for optimizing that design. And even so far as things like reusing parts of that design, reusing bits of the architecture in order to really add one more layer of optimization to your design. And secondly, the second challenge I talked about was enabling ML developers to program the FPGA. They clearly want to start with something like PyTorch or TensorFlow, and they want to do the training on GPUs in FP32. But they want to be able to evaluate that model performance on an FPGA. They don't want to turn to their FPGA designer and say, go away for a few weeks and come up with a placed and routed design and tell me how fast it's going to run. They want to be able to evaluate it far faster than that. They then want to be able to reiterate that model and reevaluate it without, again, going back to the FPGA department. They want to be able to run multiple models, ideally, on that FPGA at I say the flick of a switch. This is in runtime. And they want to be able to change models without changing the bit stream. And then another one on top of that, obviously, is with FPGAs, enabling you to change the FPGA design even to cope with modern architectures of machine learning models. On top of that, putting something together to satisfy this need, we have the situation where a lot of companies we're talking about are extremely secretive about their models and their data. So in terms of being able to answer the question, how fast will my model run on your FPGA solution, can't answer that necessarily until we've taken all of the extremely sensitive models and data on board and evaluate it and given them the answer. So we need to find a way around that as well. We're talking about balancing the ease of use with system level performance. So how do we give somebody a solution that they can test, evaluate very quickly, but at the same time evolve into a higher performance system, in the longer term. So talked about most of those things, but the last point here is supporting ever larger models. Even in latency constrained applications like conversational AI, people are trying to do more within a tight latency bound. So FPGAs have a certain limitation in terms of the size, the computational capability of the FPGA, but also the memory capacity for the weights. And we need to find ways, more creative ways, more innovative ways of fitting larger models onto those FPGAs. I talked about security around models and data, and I think I might have covered this point on the last slide just by jumping ahead. But if they are recruiting their own FPGA engineers, we've seen the kind of salaries that are being offered, particularly like finance houses, for instance. And it's not just recruiting, it's holding on to those people because they are a core asset that with a bit of churn is going to be very expensive. But also those companies are having to buy FPGA hardware before they actually try it. Totally the wrong way around. So moving on then, this is what we've done to try to address those market needs. We've created a product called Volo. In fact, we did this originally as an exercise with Intel. Intel paid us to enter a benchmark competition. And from there, we've evolved that into a fully fledged product, which we are sending into a number of latency critical applications. So as we'll see in a minute, it has unrivaled latency in the benchmarks we've addressed, but also the high throughput and power efficiency which you can get from FPGAs if you do this right. And in applications, a lot of applications, these servers are required to be energy efficient and also small rack space because they're paying a lot of money for some co-located servers, for instance, in the exchanges trading exchanges, which are very expensive. We created something which is simple to program, addressing some of those needs before, and simple to install. So I talked about the trade-off between ease of use and performance, and we can address those two options simultaneously with this product. We talked about the trade-off between accuracy and performance here. It's surprising actually how many applications you don't need to do inference at FP32. You can do inference even down to int4 we've seen, and they're even talking about 2-bit quantization for some of these applications, and still get really good accuracy. It really doesn't tail off as fast as one might think. And then future-proofing. We all know about FPGAs and their ability to deal with market or technology changes with machine learning. And that's another reason why we think this is a great platform. So I said officially the fastest. This is an example. This is our example of the benchmark between our solution and a GPU solution. So with the Intel FPGA, we achieved just under 5 microseconds for this benchmark from the STAC organization. That's the Securities Technology Analysis Center. On the right there, you've got the GPU, which is about 35 microseconds. And that just demonstrates how long it takes to get a GPU up and running before you can actually do some useful work. The other company that tried to address this benchmark was Grok, using a custom chip, and they were a little bit right of this scale. So clearly, we have that latency advantage with FPGAs, and there are plenty of applications out there when we can use it, and this is the right platform here. I talked about the need to present this in a way in which an ML developer can use it. And on the left there, you can see the ML developer can start in his PyTorch or TensorFlow environment, and then compile his design into Follow SDK. And immediately he can do cycle level and bit accurate simulations on that model to find out how that's going to perform on the FPGA. Doesn't need to buy an FPGA card to do that, doesn't need any FPGA expertise, doesn't need to let his models and data outside of his firewall. So that's addressed that need. Then when he's found his performance, he can iterate that design until he's come up with something which meets the parameters he requires, and then implement that straight onto a PCI Express card. We're currently supporting a couple of bitware cards here. We have more in the pipeline, but they can plug that card straight into a server and prove the design in hardware. That's the first stage of hardware investment, though. And so that addresses the ease of use. But then in terms of the ultimate system level performance, a lot of people we're talking to want to then improve the performance of that design by putting it and other things onto a bigger FPGA, potentially. And for that, we can give them a netlist, which they can then incorporate into their design on the FPGA. But that it really is the only area that a user would actually require FPGA design expertise. It's in that bottom right sector. And we do have customers who are just using the PCI Express accelerator card, top right. Some of the applications, financial trading was where we started, and there's a clear benefit there for companies who are trying to trade before their competitors. You see a trading opportunity, you see an undervalued stock, you want to make that trade, but if you're a little bit slow to the market, that price advantage has started to disappear straight away. And so it's helping companies to make those trading decisions. And we're not talking high frequency trading, that's nanoseconds. We're talking perhaps medium frequency trading, which is microseconds here, where every microsecond counts. That's not what we're here for. We're engineers, but we're satisfying a need there in the market. Network security is an interesting one. This is an evolving area for us, but a lot of network security doesn't need microsecond kind of responses, but apparently there are some areas out there that the faster you can do this, the better. They are using the very smallest models to try to intercept and prevent attacks. And this is just the kind of application this is for. And then finally, in wireless telecoms, we were having a conversation earlier about some surprising areas where machine learning inference is being used. Some very obvious ones, but also some very obscure ones. And this is one that I wouldn't have thought about, but it's really about, without going into depth, it's about optimizing what you've got to get a better quality or better performance by predicting future outcomes. So it saves you having to invest in a more expensive processor hardware, more memory or whatever, simply by predicting what's going to come and adapting for it. So it sounds a bit woolly and sounds a bit high level, but I think that's an area that is really opening up as people become more imaginative about how AI inference can be used. And so there, a key objective for that market is getting a product to market quickly, time to market, getting that wireless system out there, getting it used, and the ability to adapt to new models again, which, as we said, is a key benefit of FPGAs. So, driven by those applications, we have a very busy roadmap. We're building support for more FPGAs families and more boards, more operations. The more people we talk to, the more operations they want, and so we're building support for that. Larger models and ever lower latency. But again, at the moment, we're doing this with 1 bit stream on the FPGA. Well, 1 bit stream per FPGA type. In the future, we may move to more, but at the moment, we can cover all of those with 1. So I don't know how we're doing on time, but not too bad. 10. We're straight on to questions, Mike. So, do we have any questions?
Yeah, there's one thing you want.
Richard.
Yeah. Did you encounter any challenges when you look at the bit accurate simulations?
Yeah, it took a little longer than the cycle level simulation. Yeah.
It take a long time.
Yeah, we launched it end of last year, and we've had quite a few people giving us some positive feedback. Inevitably, I think people are just going to want to prove it on the hardware, and that's why we've got that quick route to a PCI Express card on hardware. But yeah, we're happy with the results now.
You probably could go up to
It's about the decision to have a single bit stream in place. So is this an intermediate step, or is this the final goal? Of course, given that FPGA is flexible,
yeah.
If you do not send hardware, what's the point? You can just have a tape out this.
Yeah. So the single bit stream at the moment allows us to cover all of the models, the layers, the operations that we're currently targeting. That's not necessarily the longer term. In fact, we've got some work going on a reconfigurable, partial reconfiguration to try to address a potential future need as we expand. But at the moment, we're able to get extremely efficient use of the FPGA with that 1 bit stream. So it's a single implementation on the FPGA, but that can run multiple models in runtime at any different time, any different moment, which is pretty much instantaneous switching. And if we want to change those models out for other models, then it's about half a second to download a new program onto that hardware to run those alternative models. So at the moment, that's satisfying customer need, and that's reflected in the benchmarks we've got. Thanks.
Well, okay. So there's a question online. If FPGAs are so good at ML inference, why aren't they more prevalent?
Well, that is a good question. I think that a lot of people are choosing the easy path, and there's no doubt that if they've been using GPUs for developing models and for training models, they've got their CUDA design environment. Those are incredibly powerful tools to persuade them to stay where they are because it's easy, it's quick, they can get to market fast. But we need to open people's minds to the opportunities for using FPGAs, where FPGAs really have an advantage. Now, the Volo tool I've spoken about is one where we have created an ML-friendly design environment. There are plenty of other areas that we've been working in, like LLMs, for instance, where we've not been able to do that. So if you want to implement an LLM on an FPGA, you've got to find your hardware designers or come to a company like us who could design that specifically for you and implement it onto an FPGA. Well, that's a lot of hassle, a lot of cost, a lot of trouble. So what we really need is to move to a situation where we can offer a design environment for a far wider range of models, where ML developers can design, test, iterate, evaluate their own models on this.
And one other question. If people wanted to start using FPGAs for machine learning, where's the best place to start with?
Come and talk to us and anybody else who's presenting today. But yes, not sure I have a better answer than that, I'm afraid.
Modesty for them. Okay, thank you very much. Thank you.